In this video, we are going to demonstrate an end-to-end external aerodynamic simulation on an electric vertical takeoff and landing aircraft using Flexcompute Flow360. Let's start from the Flow360 dashboard view. The dashboard provides an intuitive overview of items of importance, including recent simulation files, flex credit balance, the status of all projects, and quick links to example simulations. The full example library window can be opened from the top ribbon. Finally, we'll open the My Workspaces view, where you can have the project view and files view available to navigate to your geometry, mesh, and simulation. From here, we will start a new project using the New Project button on the right side of the screen. This will open up a panel to begin your project. Start by adding your project name. The solver version defaults to the latest public release, but you can use the dropdown to select previous releases. Measurement units can be changed using the dropdown to match your CAD or mesh file. Next, we will add a description for the project. While it's not necessary, this helps with quick viewing and searchability as your quantity of active projects increases. After that, we will select the method for creating the project, which can be started from a geometry, including assemblies, a surface mesh, or a volume mesh. We'll start with geometry for this simulation. You'll notice when I hover over the Browse button to upload the model, a pop-up appears that shows all supported file formats. I'll select my model and click Submit. Once uploaded and converted, I'm notified the project has been created successfully. Clicking the project card opens the Workbench layout, as shown here. The Workbench consists of a viewer region where the geometry, mesh, and simulation results are displayed, the Setup and Analysis control panel that contains all parameters and settings, the Entities panel that has all controls for visual representation of the model, the Coordinate system to change view direction, the top navigation bar to view the project tree or other quick actions like documentation, release notes, and technical support, the status bar that shows simulation progress and status, and finally, the viewer bar to switch between different view models and model selection methods. You'll notice there are tasks with a red dot on the left side of them. This means that there are warnings that need to be addressed before continuing. To see additional details on all warnings, you can open the inspector window from the bottom of the interface. These warnings will be cleared as we complete the incomplete parameters of the meshing and simulation setup. We'll start from the simulation control panel on the left sidebar. First, we will define the operating conditions by clicking on the text to open up the setup panel. You'll notice a question mark help icon at the top of the panel. Clicking this will open up the WebUI documentation to provide more information on the section that you are in. Full documentation can also be accessed here, and help icons are available in the interface throughout the full project. As this is an external aero simulation, we will leave the fluid as gas and enter a velocity magnitude of 100 meters per second, with an alpha angle or angle of attack of 6 degrees. All changes are automatically saved, so you can either close the window or click to the next step in the workflow. Next, we will define the Farfield. We'll use Flow360's automated Farfield option, which determines and creates the appropriate Farfield dimensions based on the geometry. If you have your own Farfield geometry, then you can select the user-defined option. No changes are needed for this model since the Farfield is automatically created at 100 times the model's maximum dimension. We'll move on to the mesh parameters. Flow360 uses an automated meshing process that reduces the amount of work required for the user by providing default values that are sufficient to generate a high-quality mesh for most cases. As you can see here, we only have to provide a surface max edge length of 5e-2 meters and a first boundary layer thickness of 5e-5 meters. Advanced parameters are available, but not needed for this model as the default values will create a high-quality mesh. The next step in the process is to add mesh refinements. Before adding in a refinement, we are going to create a new volume box refinement region using the Entities panel on the right side of the screen. This will help accurately capture the flow physics around the aircraft. In the Volume section, click the Add button and select Box. This will open the box editing panel where you can adjust the location and size of the box. You will notice that edits can be viewed in real time using the viewer region of the interface. You can adjust the model view to visually confirm your box dimensions are sized as expected. After that, we are going to add a mesh refinement to the box we just created by clicking the Add button next to Refinements and selecting Uniform Refinement. we 'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a spacing of 5e-2 meters and assign it to the box. We'll apply a We will also add a surface edge refinement of 1 degree to the leading edges of the aircraft. This will generate a high-quality mesh around the leading edges based on the curvature angle. The mesh is ready to be generated, which is done by clicking the Run button in the top of the interface. You can generate just the surface mesh if preferred, but we will generate this up to the volume mesh. Once completed, mesh metrics can be viewed using the Metrics Cell button in the top left corner of the viewer region to view total nodes and the quantity of different mesh cell types. We'll hide the volume box we created earlier and change the view from low resolution, which is best for quick viewing and rendering, to high resolution to show the surface mesh on the aircraft. Zooming in, you can see the refinement that was applied on the leading edges. Flow360 saves each stage of a simulation in a project tree, which provides an intuitive way to view, track, and navigate to different stages of your workflow. The project tree can be accessed by clicking on the project name at the top of the interface. This tree just has the geometry, surface, and volume mesh, but if you were performing a mesh refinement study, you would see various branches here from the same geometry, which helps organize the different mesh files. Because each stage is saved, to set up the flow solver and run your simulation, you have to create a new run using the new Run button in the top right corner. This keeps all the current parameters like mesh detail and operating conditions, but creates a new stage in the project tree that can be edited. As we go through the setup of this model, you will notice that Flow360 automates a lot of the setup for you to help reduce the amount of work required. For the boundary conditions, all surfaces were automatically assigned as a fixed wall. The Farfield that was automatically created earlier was also automatically assigned to the free stream and using the operating conditions we applied at the start of the simulation, which was 100 meters per second and a 6-degree angle of attack. Time stepping is automatically set to steady for 2,000 max total steps, which is what we will leave it at. Advanced settings are available if needed. Under Physics, we will open the Fluid panel to review the solver settings. Each section in this panel has a variety of advanced settings you can adjust when expanded. We won't adjust any for this simulation, as the defaults work well using the Spaller Almaris turbulence model with no transition model. The final step before solving is to set the reference dimensions, which will be used for non-dimensionalizing lift, drag, and other forces and moments to get the force and moment coefficients. The simulation is now ready to solve. While Flow360 does automatically create a list of surface and slice outputs to generate during the simulation, this is the time any additional outputs you would like to evaluate should be added. This includes data like volume, surface, point monitor, and streamline outputs. We won't add any additional for this, so at this point, we are good to solve by repeating the run steps we did earlier when generating the volume mesh. Clicking Run sends the simulation to Flexcompute's own GPU cluster, which is powered by the latest high-performance GPUs. The job is instantly picked up and assigned to the optimal quantity of GPUs based on the size of the mesh. As the simulation is being solved, your view will automatically shift to the Analysis Dashboard window to show real-time convergence of residuals and forces. Scrolling from top to bottom, the residuals monitor is displayed at the top, showing real-time convergence history. Below that is the statistical data averaged over the last 10% of pseudo steps for lift, drag, force, and moment coefficients, and their respective interactive plots. Each of these can also be viewed individually by clicking the corresponding section on the control panel on the left. To visualize results, we can close the dashboard window. We'll hide the volume box to get a better view of the aircraft. In the same Entities panel, you can expand the post-processing section and show or hide different results. For more advanced customization of results, you can go back to the control panel and select a result. This will open a corresponding panel where you can adjust the color map, value ranges, and result variables. Multiple components can be shown at one time. In this example, we have a variety of outputs for the surfaces of the aircraft, clips through each major axis, and isosurfaces. For exporting out your final visuals, there are additional graphical customization options available in the Entities panel under the Environment section. Background allows you to change the color of the background to a solid color, a vertical gradient, or even upload an image. Lighting and rendering configurations can also be adjusted. All data generated throughout the full workflow is available to download and share by clicking the Assets cube icon at the top right of the UI. Data from all stages can be downloaded, including the geometry, surface and volume mesh, and simulation results. Visualization results can be downloaded as a tarball to be used for further post-processing. Stay tuned for our next video, where we'll demonstrate how to perform the same simulation but using our Python API. And let us know what other demo videos you'd like to see in the future.